So if you see, the first unit is a semiconductor diode. Here in the semiconductor diode, you are having open circuited PN junction. So it is the syllabus of first unit. It is open circuited PN junction. How the PN junction acts as a rectifier. What are the different current components in a PN junction diode? So diode equation and Volt-Ampere characteristics. So VI characteristics of the diode, energy band diagram of PN diode, temperature dependence of Volt-Ampere characteristics, diode resistance. In this we are having static and dynamic resistances, and the capacitance, transition capacitance and diffusion capacitance. So these are the contents involved in your first unit. In the first unit, we are going to discuss about PN junction diode. PN junction diode. It is also called semiconductor diode. PN junction diode is also called as semiconductor diode. So I think all of you know about conductors, insulators, semiconductors, right? The conduction is more in conductors, the conduction is medium in semiconductors, the conduction is less in insulators. So here the semiconductor materials are germanium and silicon. The semiconductor materials are germanium and silicon. So in this unit we are going to discuss about PN junction diode, the working of PN junction diode, the characteristics of PN junction diode, and the temperature dependence of VI characteristics, and diode resistance and capacitance, right? So we are going to discuss all these topics. First of all, what is a diode? So diode is a semiconductor device. Diode is a semiconductor device. It has two terminals. See here, it is a semiconductor device. It consists of one P region and one N region. So it has two terminals. One is anode and second one is cathode. So anode is a positive terminal, cathode is a negative terminal. So it is the structure of PN junction diode. It is the symbol of PN junction diode, right? So it is the symbol of PN junction diode. So in our lab, you can find the PN junction diode in this format, right? So this terminal is anode and this terminal is cathode. So here we are finding the white strip line, right? Here we are finding the white strip line. So that indicates the cathode terminal. That indicates the cathode. So this indicates the cathode terminal. So this terminal is anode and this terminal is cathode. So the PN junction diode is a semiconductor device. It has two terminals, anode and cathode. So it conducts current only in one direction. It conducts current in only one direction, right? So it is a PN junction diode. See here, what is the theory of PN junction diode? What is the theory of PN junction diode? See here, we are combining the P-type material and the N-type material. We are combining the P-type material and N-type material. So all of you know the majority carriers. What are the majority carriers in P-type material? The majority carriers in P-type material are holes. The majority carriers in N-type material are electrons. So in the P-type material, the minority carriers are electrons. In the N-type material, the minority carriers are holes, right? So it is a open circuited PN junction. Here we are not applying any external voltage to this PN junction. Simply we are connecting simply we are connecting one p-type material to the one n-type material. Here simply we are connecting one p-type material to the one n-type material. So when a p-type semiconductor is joined to n-type semiconductor, the contact surface is called a p-n junction, right? So it is a open circuited p-n junction. See this diagram, it is a open circuited p-n junction. So open circuited means here we are not applying any external voltage. So simply we are taking one p-type material and one n-type material. So for this p-type material, the majority carriers are holes and the minority carriers are electrons. For the n-type material, the majority carriers are electrons and the minority carriers are holes. See here, the free electrons near the junction in the n region begin to diffuse across the junction to the p region, where they combine with the holes near the junction. So here, this is called the junction. See here, it is the junction between these two regions, these two materials, p-type and n-type materials. When you combine p-type and n-type materials, immediately the free electrons in the n region begin to diffuse across the junction into the p region. These electrons from the n region is combined with the holes in the p region. Is combined with the holes in the p region immediately, right? So it is a open circuited p-n junction. So when you join these two p-type and n-type materials, the electrons in n region, so it is ready to combine with the holes in the p region. In the same way, the holes in the p region is ready to combine with the electrons in the n region. Here the holes will combine with the electrons and the electrons will combine with the holes, right? So that is an open circuited p-n junction. We are talking about open circuit. So here we are not applying any external voltage, right? Here when these electrons combine with the holes and the holes combine with the electrons, immediately one barrier is formed across the junction. So across the junction one electric field is formed here. So across the junction one electric field is formed. So this electric field opposes the further recombination of holes and electrons. Clear? So when you combine these p-type and n-type materials, so initially the electrons will move towards to p side and the holes will move towards n side. After some time, some electric field is generated across the junction. This electric field opposes the further recombination of holes and electrons. This region is called as depletion region. This region is called as depletion region, right? So it is the open circuited p-n junction. See here, there is no external voltage applied to the p-n junction diode. Therefore, the electrons diffuse to the p side and holes diffuse towards the n side through the junction and then combine each other. Due to this, an electric field is generated by these charge carriers, right? So this electric field opposes further diffusion of charged carriers so that there is no movement in the middle region. This region is known as depletion region or space charge region or transition region. So this region is called as depletion region or space charge region or transition region. It is very important definition. What is depletion region? Right? So depletion region is The region contains the uncompensated donor and acceptor ions is called as depletion region. The region contains the uncompensated donor and acceptor ions is called as depletion region. Here these ions, here see here, these are the immobile ions. These are the immobile ions, right? So that is called depletion region. Next, there are no mobile charge carriers in the depletion region. So these are immobile. So that's why there is no current flows across the junction. So at the depletion region there is no current flows, right? Because there are no mobile charge carriers. These carriers are not moving either to this side or to this side. These carriers are not moving. So there is no current flows across the junction, right? So depletion region or depletion layer is a region in a PN junction diode where no mobile charge carriers are present. So depletion layer acts like a barrier that opposes the flow of electrons from N side and holes from P side. So the function of depletion region here, the function of depletion region is it opposes the charge carriers. It opposes the charge carriers means electrons or holes. The depletion region opposes the charge carriers from N type to P type or P type to N type, right? So it opposes the charge carriers flowing from one side to another side. So that is the open circuited PN junction. So it is a negative ion. So the N type contains the positive ions and the P type contains the negative ions. The N type contains the positive ion and the P type contains negative ions. Here, so if you see here, the P type contains holes are the majority carriers, electrons are the minority carriers, and it contains the negative ions, but the N type contains positive ions. So the region containing the uncompensated acceptor and donor ions is called as depletion region. Clear? Now we will see the working of PN junction diode. Working of PN junction diode. So it is a symbol of PN junction diode. The positive terminal is the anode and the negative terminal is cathode. See here we are combining the P-type material and N-type material. So it is a depletion region, right? So this circuit is open circuited PN junction, right? Open circuited. Here we are not applying any external voltage. So it is the open circuited PN junction. So there are two biasing conditions. One is forward biasing and second one is reverse biasing. There are two biasing conditions. One is forward biasing and second one is reverse biasing. Okay. So if you see what is forward bias, see here what is forward bias and what is reverse bias. So it is a P-type material and N-type material. Here when the positive terminal of the battery is connected to P-type and negative terminal of the battery is connected to N-type of the PN junction diode, that is known as forward biased condition. See here in the for P-type material we are connecting the positive terminal. For P-type material we are connecting the positive terminal. For N-type material we are connecting the negative terminal. So this type of connection is called forward bias connection. Forward bias. See here So it is the equivalent circuit of the PN junction diode. In forward bias condition, the diode contains some internal resistance. So it is the internal resistance of the diode, and it has battery, right? So it is the internal circuit of the PN junction diode. So in the forward bias, the positive terminal is connected to p-type material and the negative terminal of the battery is connected to n-type material. Clear? So what will happen? So if you connect the external voltage to the PN junction diode, what will happen? See here, the applied potential in external battery acts in opposition to the internal potential barrier, which disturbs the equilibrium. Under forward bias condition, the applied positive potential repels the holes in p-type region so that the holes moves towards the junction, and applied negative potential repels the electrons in n-type region so that the electrons move towards the junction. You see this diagram. So in the forward bias condition, so what is the charge of this p-type material? The charge of p-type material is positive, so it is connected to positive terminal of the battery. So here we are having the same charges, right? So it is a positive charge and it is the battery positive terminal, it contains a positive charge, right? So here we are having the same charge. So due to this same charge, the holes in the p-type material are trying to break this junction. So here it is a depletion region, right? So when you combine this p-type material and n-type material without having any external voltage, some depletion region is formed, right? So this depletion region opposes the further recombination of holes and electrons. When you apply the external voltage, due to this same charge, positive charge and positive charge, due to the same positive charge, these holes are trying to move towards this n-type material and will recombine with the electrons in the n-type material, right? So in the same way, here the n-type material, it contains a negative charge. So the battery negative terminal, it contains a negative charge. Here also the same charge, right? So due to this same negative charge, here the electrons are repelled towards this battery, right? So these electrons trying to move towards this p-type material. So when you apply this external voltage, due to the same charges on both sides, these holes are trying to break this junction and these electrons are trying to break this junction, right? So for example, if you apply 0.7 volts, for example, if you apply 0.2 volts or 0.3 volts, so at this, if you apply 0.2 volts or 0.3 volts, this voltage is not sufficient to break this junction. This voltage is not sufficient to break this junction, right? For example, if you apply greater than 0.7 volts, here if you apply 0.7 volts, greater than 0.7 volts, immediately in silicon material, the junction will break. That means this voltage is less than the external voltage. The voltage across the junction, that is less than the external voltage, right? So if you apply 0.7 volts or greater than 0.7 volts in silicon material, this junction will break. If this junction breaks, then immediately the holes in the p-type material will move towards the n-type material and recombine with the n-type material. In the similar way, the electrons in the n-type material will move towards the p-type material and recombine with the p-type material, that is recombine with the holes in the p-type material. So that's why here the movement of charge carriers takes place. The movement of charge carriers takes place. The holes are moving to this n side and the electrons are moving to p side, right? So due to this external battery, so then the diode starts conducting. We can say that if this junction breaks due to this external voltage, we can say that the diode is in conduction state. The diode is on, right? So the current flows through the diode. See here, when the applied potential is more than the internal barrier potential, the depletion region and internal potential barrier disappear. So when the external voltage is more than the internal barrier potential, then the depletion region will disappear. So once the barrier potential is eliminated by the forward bias voltage, so the junction resistance becomes 0. Therefore the current flows in the circuit. So when the junction breaks, here the junction resistance will be 0, right? So in the forward biased condition, the diode conducts. In the forward biased condition, the diode conducts, right? So we will see in the reverse bias what will happen in the reverse bias. So these are the forward bias characteristics. See here, these are the forward bias characteristics. So the semiconductor materials are germanium and silicon. Generally, we prefer silicon material. So for germanium, the cut-in voltage is 0.3 volts. That means for germanium material, if we apply the 0.3 volts external voltage, the junction will break and the current flows through the diode. So that's why up to 0.3, see here, up to 0.3 there is no current flowing through the diode. Here x-axis is the forward voltage and y-axis is the forward current. We are discussing about forward characteristics. In the germanium diode, so the current flows for 0.3 volts, right? This voltage is called as knee voltage. Knee voltage. Knee voltage means in the forward biased condition, at which voltage the junction breaks and the forward current flows through the diode. That voltage is called as knee voltage. Whereas in silicon diode, that voltage is 0.7 volts. Here in silicon diode, up to 0.7 volts, there is no current flows through the diode. When it reaches to 0.7 volts, the depletion region will disappear and the charge carriers moving from p side to n side and n side to p side. So due to the flow of charge carriers, the diode current will flow. Right? So that is in silicon diode, 0.7 volts is the knee voltage, whereas in germanium diode, 0.3 volts is the knee voltage or cut-in voltage. The other name for knee voltage is cut-in voltage. Cut-in voltage, knee voltage, everything is same. So for germanium, the cut-in voltage is 0.3 volts. For silicon, the cut-in voltage is 0.7 volts. So that means here we are applying the external voltage, right? So in germanium, if it is 0.3 volts, the diode current will flow. In silicon, if it is 0.7 volts, diode current will flow, right? So when it comes to, okay, so these are the forward characteristics. So when it comes to reverse bias, okay, so see the definition of knee voltage here. The voltage at which diode starts conduct is called knee voltage or cut-in voltage. That is in forward biased condition. So knee voltage, it occurs in forward biased condition. So the voltage at which the diode starts conduct is called knee voltage or cut-in voltage. Okay. So cut-in voltage is 0.3 volts for germanium and 0.7 volts for silicon. So if you see the reverse bias, see here, if you compare the forward bias and reverse bias, here the negative terminal of the battery is connected to P-type and the positive terminal of the battery is connected to N-type. That is called as reverse bias condition. See here, the negative terminal, here the negative terminal is connected to P-type material and the positive terminal is connected to N-type material. The negative terminal is connected to P-type and the positive terminal is connected to N-type, right? So this type of condition is called reverse biased condition. So here the P-type has positive charge, here the negative terminal has negative charge, right? So opposite charges. So these two opposite charges attract each other in similar way. Here the two opposite charges, see here, N-type having negative charge and here they are having the positive charge. So here these two charges will attract each other. So that's why in the P-type material the holes are trying to move towards this negative terminal. The holes are trying to move towards negative terminal and here the electrons are trying to move towards positive terminal. Then what will happen? So here there is no charge carriers are moving towards the junction, right? So here these charge carriers are moving towards the battery, here these charge carriers are moving towards the battery. So that's why if the electrons and here, so here the holes and here the electrons are not trying to move towards the junction. So that's why there is no flow of charge carriers. There is no flow of charge carriers. That means here the depletion region will increase. Here the depletion region will increase. In forward biased condition, the depletion region decreases. In forward biased condition, the depletion region decreases because the holes and the electrons will move towards the junction and recombine each other. But in this reverse biased condition, the depletion region increases. The depletion region increases, right? So that's why there is no flow of current in the reverse bias. There is no flow of current in the reverse bias because these charge carriers are moving in this direction and these charge carriers are moving in this direction. So there is no flow of charge carriers across the junction. That's why we can say that in the ideal condition, in the reverse biased condition, the current will be 0 in the ideal case, right? So that's why we can say that the diode conducts only in one direction. The diode conducts only in one direction, that is only in forward biased direction. Diode does not conduct in the reverse bias condition. Diode does not conduct in the reverse biased condition. So diode conducts only in one direction. So if we see the reverse bias characteristics, so reverse bias characteristics, see here. So here the diode current is in microamperes, whereas in forward biased condition the diode current is in milliamperes, right? So the minority carriers, electrons in the p region and holes in the n region, wander over to the junction and flow towards their majority carriers are giving rise to small reverse current. So this current is known as reverse saturation current I0. So reverse saturation current, it is called reverse saturation current. So due to the minority carriers, the current flowing through the diode, that current is called as reverse saturation current or minority carrier current. For example, in the p side material, the minority carriers are electrons. In the n side material, the minority carriers are holes. So due to the flow of these minority carriers, the reverse saturation current is flowing through the diode. So that is called minority carrier current or reverse saturation current. So here x-axis is reverse current, it is in microamperes, it is very less. Sorry, x-axis is in reverse voltage, y-axis in reverse current, reverse bias current. So if we see the complete VI characteristics of a PN junction diode, one second. It is not uploading. Okay, so these are the VI characteristics of PN junction diode. So diode conducts in forward biased condition, right? So these are the forward bias characteristics. These are the forward bias characteristics. So these are the reverse bias characteristics. So in forward biased condition, we are having the new voltage. In the reverse biased condition, we are having the breakdown voltage, right? So these are the VI characteristics of the PN junction diode. So in the today's session, we have discussed about the complete working of PN junction diode. If you have any doubts, you can ask me.